friends, this is Mrs. Wrona here. I'm going to go over how do we solve these mostly SCP-5 questions, but we'll practice the SCP-4 with drawing the LOL diagram with energy when we have work present in the problem. So in the 2025-2026 packet, this is on page 46. If you're looking at this in future years, it might be on another page, but this is a problem where an arrow is shot straight up from the ground and reaches a maximum height, but there's a force of air resistance acting on it over that entire height that it travels. So let's draw our energy bar graph. The initial energy, I like to look here. I was telling some of my students, right under there, right when it's shot, that's an important part of your LOL diagram. So right when it's shot would be before it's gone up at all. So there's 0 UG. It hasn't actually gone up, but it's right when it's shot. I can also, look at the picture. It doesn't have a height yet. So the initial point, there's no height, so no UG. But when it's shot, it has a lot of velocity. So I'm going to make this 4 bars. You can make it 3, you can make it 2. I probably wouldn't make it 1, but we're going to start with lots of kinetic energy because it's right when it's shot from the ground. Now it's going up, so if I look over here on the final LOL, we're going to do it max height. Max height, we know a physics concept is that objects stop at the maximum height, so the kinetic energy is going to be 0, and so all the energy is going to be gravitational potential energy. However, the new part in these problems with work is that there's air resistance. So if there is a force acting over a distance, then we know there's work being done, right? If we look down at the bottom of the page, there's this equation for work. Work is when a force is acting over a distance to either add energy or remove energy from a system. So if we think about air resistance would be pushing down on the arrow and the arrow is traveling up. So that's going to cause energy to be removed from the system, right? If there was no air resistance, this arrow would go higher. And so we would represent this as energy leaving the system. So you draw an arrow going out of the circle. And you can decide how much energy it's going to be for the SCP-4 portion. If you want it to be like 1 block, 2, 3, I wouldn't make it all of it, right? Because it does actually go up. So I might make 1 block of energy leaving the system. So over here, I started with 4 blocks of energy. I took away 1, so that's minus 1. So I'm going to have to end with 3. So my UG over here has 3 bars of gravitational potential energy. So if I start with 4, I take 1 away, end with 3, energy's still conserved, right? It's accounted for across my LOL. It doesn't mean the initial and final are the same. So down on the line, you write what kind of energy type. Initially, it was all kinetic energy, minus some energy was lost. So that's minus work, negative work. And at the end, we end with UG, gravitational potential energy. So the line below that, I break that into the actual equation. So K, we know, is 1/2 mv squared. If you ever forget that, it'll be given to you as well. So it's down there at the bottom of the page. Minus work. Work is FD. The F stands for force. The D stands for distance. And UG is mgh. Again, all of those are given at the bottom of the page. So what you just wrote here, the whole point of doing this is now our energy equation we're going to use to solve our problem. So the problem says calculate the launch velocity of the arrow. So we're looking for what is that initial velocity of the arrow. So we're going to write this equation again down here. 1/2 mv squared minus FD is equal to mgh. So you have to decide when you set up these problems if the energy is added or removed. Since it's removed, that's what made this minus. If it was adding energy, it would be plus work. So now I just start plugging in my values. 1/2 m is mass in kilograms. So if I go up top, that's the 0.75 kilograms. V is velocity. That's what I'm looking for. What's the launch velocity of the arrow? Minus F is the force acting on it outside of the system. So what's the force in this case? That's that air resistance. So they gave us that in newtons, so 0.02 times over what distance was that force applied? Over that whole distance it was traveling up, so 21.6 meters, is equal to the same mass. Again, this is at the end. The arrow didn't gain or lose mass, so 0.75. G is the gravitational field strength on the planet, so 9.8 on Earth, times the height. How high did it go? That was given up here, that same 21.6 meters. So after this point, the physics is done and we're using algebra. So on the left side, we get 0.375 v squared minus, if I multiply these together, I get .432, I think. I'm looking at an answer key. I don't actually have a calculator in front of me. 158.76. And now a lot of people want to add these two together. We can't do that because they're not like terms. So what we're going to do is add this to both sides. So plus 0.432 plus 0.432. These will cancel. And so you'll get 0.375 v squared is equal to 159.192. Divide by 0.375 and you get v squared is equal to 424.512. Take the square root of both sides and you get a velocity of 20.6 meters per second. So that was the initial launch velocity in order to get that arrow to go 21.6 meters per second.